So now let's say we have, let's say this case. So this is the circle with let's say the center given as this, and should be like that. And say we have the object moved from point A, let's say up to point B along the circumference of the circle with the constant radius. Much as you understand that a typical circle must have actually the common center as well as the common radius. And let's say the angle that has been swept at the center, that is said to be the angular displacement, is given as theta. Let me use another ink here. So now is given as the angular displacement is said to be angle theta in that way. And now from point A to point B, let's say the object at a point A has been traced with initial angular velocity, which is given as the omega I. And to point B, the object has been traced with the final angular velocity given as WF. And let's say the time takes for the object to move from point A to point B is given as, now let's say t. Mind you, the object is going like this, and the time takes has been given as, let's say, a t. Now, much as there is a change in angular velocity, it means the object has accelerated. Hence, let's say the acceleration is given as, let's say, alpha, that is angular acceleration. So just like the way we discussed about, now let's say, assuming that the object is moving at a constant acceleration, if this is the case, which means at each and every point there is an equal rate of change of the angular velocity per unit time. So that's the object moving at a constant, let's say, angular acceleration. It's just like the way we discussed about the object moving at a constant linear acceleration. So how should you be able to have to describe or to analyze the object of motion now using the equations of kinematics? So now, much as the object is moving at a constant angular acceleration, then we can be able to analyze the motion using the equations of kinematics. So you understand, we have a first equation which is given us, which is for the average velocity. So the average velocity is given as v is equal initial velocity plus the final velocity divided by 2, of which this is the initial and this is the final velocity. So now in linear motion, this one will be now being given as omega, that is the average angular velocity, is equal to the initial angular velocity plus the final angular velocity, and that is divided by 2. So this will be the equation, and that is to analyze the motion moving in a circular path, and with respect to the linear motion concept. And also we have another equation that is that of should be average displacement, which is given as S is equal to U plus V over 2 in the times time. So now if this is the case, then mind you, this is the displacement initial final, this is the time, choose a constant. So now, which means in a circular motion we can have to express we can have to express it as the angular displacement given as theta is equal, now should be like this, actually initial angular velocity plus the final angular velocity divided by 2 and the times time. So now times time. Now this is the formula. This is the formula in circular motion and with respect to the linear motion. So which means if we have the angular displacement, we have the initial angular velocity and the final angular velocity, we can be able to have time using that formula. So take note of that. And also we have another equation, and which is we have what you call acceleration formula, which is given as v is equal to at plus u, where this is the final velocity, acceleration, time, and this is the initial velocity. So what is that in circular motion? We'll have omega f is equal to angular acceleration in the times time plus the initial actually angular velocity. So this is the formula. So which means we can be able to have angular acceleration. Now should be using this formula. So much as we have the final angular velocity at time as well as the initial angular velocity, can be able to have that one in that case. And also we have the displacement formula. So what is that one? So we have it as displacement is equal to ut plus half ad square. Now in circular motion we'll have it as the omega, that is angular displacement, is equal to initial angular velocity plus half now angular velocity a time square. That's how we should have to express that one up to. So much as we have, let's say, initial angular velocity up to the angular acceleration in time, can be able to have the angular displacement using that formula. Actually, mind you, here we have times t, so should be a times t here. So bear that in mind. And we also have what we call another formula, which is given as v square is equal to u square plus 2as. So in this case, this actually a formula now will be expressed as actually omega f square is equal, that is a final velocity angular, actually it should be final angular velocity square is equal to the initial angular velocity square plus 2 angular acceleration times the angular displacement. So take note of that. So which means if we have the final initial angular displacement, you can be able to have angular velocity, angular acceleration using actually that formula as well. So that's how you should have to understand about expressing the equations of motion actually in a circular motion for the object moving in a uniform circular motion, and with respect to the equations of motion in a linear motion. So take note of that. I understand that the angular velocity is has to be given in lad per second. This is the basic unit for angular velocity. But some typical problems, you can be given the angular velocity in terms of, let's say, rev per second. Let's say that's the case. Can be you can be given in terms of revolution per second. So which means it is your humble duty to convert that one into actually lad per second. And it can also be, let's say, expressed as the degree per second, or whichever, then, but you should be able to express that one into this basic unit. And also you should have to understand that the unit measure for angular acceleration is given as should be a lad per second square. So given in whichever the unit, then you should have to express that one into the basic unit. And also the angular displacement has to be given in, should be in lads, has to be given in lads. So which means sometimes can be given in terms of the degrees. You should be able to express that one into radian measure. It can also be expressed in terms of, let's say, revolutions. So you should also be able to understand on how you can be able to convert from radian measure to revolutions. So bear that in mind. Now let's go into some sort of questions related to actually a moving of the object at a constant angular acceleration and making use of the equations of motion. So let's say this is the question. The question says that after fixing a flat tire on a bicycle, you give the wheel actually a spin. A, if its initial angular speed was 6.35 rad per second, and it rotated about 4.2 revolutions before coming to rest, what was its average angular acceleration? And B, what was actually, for what length of time did the wheel rotate it? So what are the given parameters in this question? Now in this case, we have the initial angular velocity, which is omega I, being given as 6.35 rad per second. And in this case, we have also the final velocity, because it says that coming to rest. So which means the final position was actually the final velocity is given as that is angular final velocity should be angular actually final angular velocity is given as 0. And we have the angular displacement that has been expressed in terms of revolutions. So 14.2 rev. Of course, we should have to express that in radian measure. And of which we know that 1 rev is equal to 2 pi. And how about the 14.2 rev? So now, which means we'll have 2 pi times 14.2. Now should be revolutions. So with calculator, what is 14.2? 14.2 now times 2 pi. What is that? So which means we'll have it as 89 point, should be 25, let's say should be 26 rad. So that is the actually angular displacement. That is the angular displacement. Now the question says that what was its average angular acceleration? That is, now we are looking for alpha. So what is the formula in those equations of motion? We have it as angular, actually a final angular velocity is equal to alpha times time plus the initial angular velocity. So you'll be able to have that particular alpha in that formula. So now the question C, actually B, says that what will actually, and of course this formula won't work because we do not have the time. Then if that's the case, we should use this formula. that is final angular velocity square is equal the initial angular velocity plus 2 alpha angular displacement. You'll be able to solve for that one. So take note of that. Now, having calculated the angular acceleration, now the question B says that we should have to calculate the time it takes. So it's either we can use this formula, the one I've recently removed it, as the final angular velocity is equal angular acceleration time plus the initial angular velocity. So you'll be able to have time, or else the formula for angular displacement that is being given us now should be angular displacement is equal to u now should be initial angular velocity plus the final angular velocity divided by time, actually divided by 2 times time. You can also use this formula as well, since we have the angular displacement initial as well as the final, can be able to have time using that formula. So take note of that, or else we can also use this formula, and that is angular displacement is equal initial angular velocity times time. So should be initial times time plus half alpha at square. You can be able to have time using this formula as well. So take note of that. Now let's say we have this question as well. A ceiling fan is rotating at 0.96 rev per second, and when turned off, it slows uniformly to a stop in 2.4 minutes. So how many revolutions does the fan make in this time? So we are looking for angular displacement. Mind you, angular displacement is expressed in terms of revolutions, or actually degree measures, as well as in terms of the radians. So in this case, we are looking for revolution, actually angular displacement, and we have been given the initial angular velocity, which is given as 0.96 rev per second, and of which it has to be in rad per second. So which means we'll have to convert 0.96 rev should be in radians. So what is that one? We understand that now should be 1 rev is equal now should be 2 pi, rad. How about 0.96 actually rev? Now should be, now we'll have it as should be unknown. Really, actually it has to be, should be less in that case. So we'll have this one times that one, so which means we'll have to multiply 2 pi rad and by 0.96. So 0.96 times 2 pi so now which is given us now we should have it as 6 rad per second. Now this is the initial angular velocity in its basic measure, and we are told that the time is given as 2.4 minutes, so should be that. Now the time has to be converted into seconds, so I understand that 1 minute is equal to 60 seconds. How about 2.4 minutes? Then we'll just have to multiply 60 times 2.4. Mind you, you should have to know how you can be able to convert these units. I understand you actually you know what is happening. So in this case, we have it as 144 seconds. So that is the time in seconds. So now the question says that we should have to calculate the angular displacement rather, and that being given as that. So how should you have the angular displacement if this is the case? So the formula should have to use should be given as the angular displacement is equal to initial angular velocity times time plus half. Now should be, and this formula won't work because we do not have the angular acceleration, so it will not work. So which one will actually work best if that's the case? And by the way, we also have the final angular velocity, which is because we are sure that uniformly until it is stopped within this time. So which means the final angular velocity has to be 0. So we should have to get it like that. Of which we are looking for the angular displacement. So this formula will work best as well. That is the final. So let me just have to. So which means the time is given as 144 seconds, and the initial angular velocity has been expressed as this. So now we are looking for the angular displacement. That will be given as now the final angular velocity square is equal to the initial angular velocity square plus 2 alpha should be that. And also, of course, this formula won't work because we do not have actually that value. Of course, it's true more, that's the principle behind. So we'll have this one, and this is angular displacement. So we do not have the angular velocity, actually angular acceleration, so it will not work. But of course, for us to use this formula, then we should have to ensure that we have angular acceleration. That will be obtained using this formula. So final angular velocity is equal, now should be angular acceleration times time plus the initial angular velocity. So since we have these, and we have these, and we have the time, we can be able to have this one, and I'll have to substitute it here, and you'll be able to solve for the angular displacement. But I understand that the angular displacement will be obtained in terms of lads. So that is, and you'll be required to convert it from the lad to revolutions. So take note of that. Or else we can also have it directly from this formula. And we can also have it directly from this formula. So that is angular displacement is equal to initial angular velocity plus the final angular velocity divided by 2 times time. This is also the best form you can have to use as well to have that and that, but that's the principle behind. Now the bad question actually B says that find the number of revolutions the fan must make. Now Strumo the angular displacement now should be using the result from part A. So what have we obtained from part A? We have obtained the number of revolutions from part A, of course. That's the displacement, of course. Now, find the number of revolutions the fan must make for its speed to decrease from 0.96 rev per second actually to that one. So now, from a part A, we need to have acceleration. So we need to have acceleration, that is angular acceleration, and such that we have this one as the initial angular actually speed or velocity, and this is the final. Now we are looking for the angular displacement, and of which the formula will be given as the final angular displacement is equal now the initial angular displacement square plus now 2 angular velocity in the times angular displacement. So this is the formula that you should have to use to have that out. And what if we also have this question as well? We should have to see. So a discus thrower starts from rest, so which means the initial angular velocity is given as L, and that begins to rotate with angular constant acceleration. Now that is actually alpha is equal to 2.2 rad per second square. So that one. So how many revolutions does it take for the discus thrower's angular speed to reach up to now? That is the final angular velocity given as 6.3 rad per second. Now we are looking for the angular displacement that is should be expressed in terms of revolutions. So how should we be able to have that now? We'll use this formula. Final angular displacement square is equal, so should be a final angular velocity square is equal to the initial angular velocity square plus 2 alpha angular displacement. So you'll be able to have the angular displacement. Of course, it will be given in rads, then you have to convert it into revolutions. And how much time does this take? It means, or we are looking for the time takes. So with the given information, we use either we can use either this formula, that is the final angular acceleration should be a velocity is equal to alpha times time plus the initial angular velocity. Actually a velocity can be that. You'll be able to solve for time, or else from the displacement actual formula you can also have to look over that as well. So that's how you should have to understand about the rotational kinematics.